Good evening, everyone. I'm Ruth with you today, and I'm delighted to welcome you to the day 4 of the tutorials on 5G Essentials. So I hope you have been having a great learning experience so far. On Monday, the day 3, we explored 5G use case and applications, covering its role in smart cities, healthcare, industrial automation, and mission critical communications. We also discussed some of the key challenges in the large scale 5G deployment. Okay, that's what we have. No, that's what we have got to understand on Monday's session. And today, our focus is going to shift to key technologies that enable 5G, including network slicing, edge computing, and radio access innovations. To continue from where we left off on Monday, we have Venkatesh from Niral Networks, who will guide us through the core aspects of 5G.
Good afternoon, everyone. Like in this today's session, I'm going to cover the VoNR, IMS, and 5G network slicing. Now we will start with IMS and VoNR. Let's start by understanding IMS and its role in modern telecom networks. First we know what is IMS. IMS stands for IP Multimedia Subsystem. It is an architecture that enables multimedia services such as voice, video, messaging, and conferencing over the IP-based networks. Like unlike traditional circuit switched voice calling in 2G and 3G, IMS allows voice calls to be carried over packet switched networks like 4G LTE and 5G as well. IMS was introduced to replace a traditional telephone infrastructure and it provides a unified communication framework. It works with both wireless and wired network and it ensuring users can make high quality calls over cellular, even with Wi-Fi and even both 4G and 5G it will support. And role of IMS in OLT, V1 and Wi-Fi calling. Like IMS plays an important role in supporting modern voice services such as VoLT. VoLT stands for Voice over LTE. IMS enables high definition voice calls over 4G by routing voice traffic through IP instead of traditional circuits. In 5G, it is called it as a VoNR. That stands for Voice over New Radio. Like in 5G network, IMS is responsible for handling voice and video calls over the 5G standalone core network. And even it supports IMS supports over the VoWi-Fi call also. That stands for Voice over Wi-Fi. With IMS, users can make a carrier-grade voice calls over the Wi-Fi network when cellular coverage is weak. Even IMS provides a seamless experience by allowing users to switch between like a VoNR, VoWi-Fi, and VoLTE as well. Then why IMS is needed? With the move to 4G and 5G, everything shifted to IP-based communication, like including the voice calls. IMS ensures that the voice services remain available in all the IP networks. Some of the key reasons for IMS is important, like it eliminates the need for legacy circuit switched voice network, and it unifies voice, video, and messaging services over IP. It provides better scalability and flexibility for telecom operators. It work across multiple access technologies like LTE, Wi-Fi, and even 5G. IMS acts as a bridge between the traditional telecom and modern IP-based communication. Some of the key benefits of IMS are like it supports the services like VoLT, VoFi, and even MCX services also it will support. MCX it stands for the mission critical applications. Like IMS ensures that users can make voice calls over LTE, Wi-Fi, and even mission critical communications. It uses a SIP for signaling and RTP for media transmit, and IMS relies on SIP to set up and manage the calls, while the RTP handles the actual voice and video transmission. It ensures QoS for real-time traffic. Like IMS assigns a different priorities to different types of traffic. It ensuring that voice calls get the lowest latency and the highest reliability. And it enables a seamless handovers between the LTE, Wi-Fi, and 5G. With IMS, a call started on LTE can seamlessly transition to a Wi-Fi network or 5G without dropping. Next, we will move into the IMS architecture and how its components work together to deliver these services. Like this is a high-level overview of IMS architecture. IMS consists of multiple functional components that work to deliver IP-based voice and multimedia services. These components are categorized into different layers, interacting with 5G core and 5G RAN and the Internet DNN. Let's break this architecture into let's break this architecture into three key sections. One is the 5G core and RAN. Like this will handling the connectivity between the user and the core network. And next is the IMS network. It manages multimedia services and managing signaling and session control and media signaling. And it helps to connect to the external network also. Like if IMS concepts want to be connect to the public switched telephone network, that stands for the PSTN. And like in the legacy 2G and 3G, they're following the PSTN for the voice services. It follows the SS7 protocol. In 5G core and RAN, starting from the left, we see that user equipment, which could be a 5G smartphone, tablet, or any IMS-enabled devices. This U is connected to that G-Node B over the N1 interface, which carries the signaling messages. Next, the G-Node B connects to the ASIC AMF over the N2 interface, and AMF is responsible for handling the like authentication, mobility, and session management. And in the for media traffic, the data packets will flow through the UPF over the N3 interface. This UPF is responsible for routing and forwarding the actual user data to that IMS core network. And then SMF is that it's to establish session. SMF interacts with UPF over the N4 interface, and it ensuring the proper QoS profile for IMS sessions. At this stage, the user is connected to the core network, but IMS services are not yet initiated. For that, UE must register with the IMS core network. Now, moving to the IMS network in the green section, there is where the actual IMS functionalities takes place. Here you can see that PCSF. PCSF stands for Proxy Call Session Control Function. This is the first point of contact for any IMS devices. It acts as a SIP proxy and ensures all SIP signaling from the UE is routed correctly. It is also applies the some of the securities, and it controls the quality policies also. Next we move to that ICSF. ICSF stands for Integrating Call Session Control Function. It is responsible for determining which SCSF should handle the user request. It queries the HSS for this information. Then one other network function of IMS is SCSF. SCSF stands for Serving Call Session Control Function. Like this is the most critical entity in IMS. It handles the user registration, authenticating the users, and maintaining the session states as well. It also interacts with the application servers like TAS. TAS stands for the Telephony Application Server. It is the TAS is used for the call forwarding feature. And next is the MRF. This MRF stands for Media Resource Function. It is used for conferencing, like a conference call and a media announcement, like any media announcement and such kind of functions. This MRF is useful. And next is that BGCF. BGCF stands for Breakout Gateway Control Function. It decides whether a call should be routed within the IMS network or it should be forwarded to that PSTN, that means the 2G or 3G network. So that functionality will be taken care by this BGCF. And next is the MGW. MGW stands for Media Gateway. Like if the calls needs to go outside the IMS network, this media gateway converts that IP-based calls into the circuit switched calls for that PSTN compatibility. And this is the external. Apart from this, at the far right, we have the interconnects to that public network. It's known as a IMS voice DNN, like which comes to that IMS to the external VoIP or PSTN or other IMS networks. And then here we also see that internet DNN, which allows the IMS services to interact with any web-based application as well. So to summarize this IMS architecture, 5G core and RAN handle the connectivity from the user to that IMS core, and IMS core provides the SIP signaling, media handling, and call control using the CSA function. And it interacts with external for the PSTN and like for the legacy 2G and 3G voice network as well. Okay. Now we'll move to the next slide. CSAF functionalities. Now that we have discussed the IMOS architecture clearly, let's discuss focus on one of its core components, CSAF. CSAF stands for Call Session Control Function. Like CSAF, it is a fundamental part of that IMS architecture. It is responsible for handling SIP signaling, session control, and user authentication. Like it ensures the smooth multimedia session management. CSAF is further divided into three key functional entities: PCSAF, ICSAF, and SCSAF. Each of these has a specified role in the IMS call handling and registration. Now let's start with PCSAF, that means the proxy call session control function. It is the first network element a user interact with when accessing the IMS services. Like it acts as a SIP proxy and enforces the security and QoS policies. Some of the key functions of the PCSAF are it forward the SIP session forwarding to the SCSF. Like it routes the SIP message to the appropriate SCSF. And another is the QoS reservation. It ensures the quality of service for media session and any emergency allocation. Like it supports the emergency calls by prioritizing them. And this is the first point of contact with the UE, and it will encrypt and integrity production. That means it will secure SIP signaling. If any of that SIP messages transfer between the like a user agent, that means the mobile and that SIP server, it will be encrypted with either the IPsec or TLS. And it generates the CDR. Like CDR stands for the call detailed records. It's used for the billing and like any analytics. We can use this CDR data. Like PCC ensures that messages are securely forwarded to the right IMS entities, and it helps to maintain the QoS profile. Next, we move to that ICSF. ICSF stands for the Integrating Call Session Control Function. Like it acts as a middleman between the PCSF and SCSF. It is responsible for coding the like user information and assigning the SCSF for call processing. Like some of the key functionalities of that ICSF is like it's check user has is it queries the home subscriber server to verify the user identity, and then it will allocate the registered SCSF. It assigns a suitable SCSF for the session handling, and it will act as a gateway for roaming subscribers. It helps to connect the roaming subscriber to their home network as well. ICSF is particularly important for its roaming users, and dynamically it will allocate the resources also as well. Next, we move to that SCSF. SCSF stands for Serving Call Session Function. It is the most important entity in IMS because it manages the session control, user authentication, and service execution. Like some of the key functionalities of the SCSF are it is used in the registration process, like it handles the user registration in IMS and security and authentication. It will authenticate the user with the help of the HSS, and like it have the user services handling. It enforces the service policies and executes call control logic. And this also generates the CDR. It helps with the billing and analytics. Like in short, we can CSF it will act like a SIP server between the that maintains session states, applies service logic, and ensure secure communication. Like how these components work together. Like when a UE initiates a IMS session, PCSF receives the SIP request and it forward to that ICSF, and ICSF queries that HSS about that user profiles, and it assigns an like appropriate SCSF, and in SCSF authenticates the user and manages the session. Now let's discuss another critical component in IMS, that is that HSS. This HSS stands for Home Subscriber Server. Like it is a database in IMS. It stores and manages the subscriber related information. It plays an important role in authentication and like service authorization and even the mobility management. Some of the key functionalities of HSS are user authentication. It verifies the users during the IMS registration and using the authentication vectors like a key, OPC, and it will some of the important parameters in IMS are like IMPA and IMQ that will be covered in later of this section. And it works with the SCSF to perform the security checks. Then subscriber profile management. It stores and manages the user subscription data and determines which IMS services a subscribers can access. And call routing and service authorization. Like it provides a user profile information to the SCSA for call routing, and it ensures that only authorized services are provided to subscribers. Next is the mobility and location management. It tracks the registered network location of the users. That means it's simply but it will know the IPs of the users. And next is the IMPU and IMPA. This is that some of the identifiers for of the IMS users. Like it tracks and registered it's like IMPU is a public user identity. It's like kind of a phone number. It will be looks like a URI. And next is that IMPA. It is IMPA stands for that IMS private user identity. Like it is a unique identity for the authentication. Like the accesses ensures the proper mapping between the IMPU and IMPA for security and service continuity. Next is that service subscription control. Like it manages access to the VoLT, VoNR and voice calls and video calls and other IMS services. It determines whether a subscriber is allowed to use a specific IMS features or not. Now if you look at this diagram, you will see that Niral 5G core includes several network functions like AMF, which manages the user registration and mobility, and SMF for session management, and PCF for the policy control, and some other network functions are here. Now, when it comes to that IMS, we have three components like a proxy CACF, integrating CACF, and serving CACF. So these elements can handle the user authentication and to call routing and service authorization. Like here, you can see some of the key network interfaces are like N1 and N2 interfaces. It connects the user equipment and the core network. That means the AMF, and N3 interfaces between the RAN and UPF, which handles the user data transfer, and N4, like it helps to coordinate with between the SMF and UPF for managing the sessions, and N5 interface. N5 interface between the PCF and PCCF for handling managing the policy control, and the N6 interface that is between the UPF and any of the data network. Like this N6 interface where user data exists the core network and connects to the external application like a VoNR and other VoLT and other IMS related services also over this N6 interface. Now let's go step by step on how IMS interacts with the 5G code to establish a call or a session. First, when a user turns on their phone, it tries to register. That IMS communicates with the AMF in the 5G core for authentication. Once it's registered, if the user tries to make a call or send a message, PCSCF like it ensures that the signaling the route. Like once the U is registered, if the user tries to make a call or send a message, PCSF ensures the signaling is routed correctly, and then the PCF applies the policies to the ensure the like right quality of service is provided for that call. Finally, the media packets like actual voice or video, that means the RTP packets are transmitted through the UPF. Now let's move to that IMS identities. In IMS, like user identities is an important role in authentication, like in authentication, authorization, and even the service provisioning. There are three main types of identities used in IMS, like which are stored in the ISIM. Like ISIM stands for the IP Multimedia Services Identity Module. Like in the SIM card, there are two things will be there. One is the USIM and ISIM. Like USIM, it will store that like some of the 5G uh, 5G, 5G credentials, like it may be the IMC key and OPC. And in the same way as in ISIM, it will store the IMPU, IMPA, and some of the authentication parameters like a key and OPC as well for the IMS authentication. Now let's move to that IMS private identity. Like this is the unique private identifier assigned to the user by the operator. It is never shared with the other users, like and is used for the authentication purpose. Like we can think of it is like a username that network uses the internally to verify the user subscription. And next is the IMS public identity. Like unlike the IMPA, Publicly, it identifies what other users see when they communicate. This is similar to a phone number. It allows the users to reachable for voice calls, video calls, or messaging services in IMS. And next is this public service identity. This is used to identify specific IMS services rather than individual users. For example, a PSA should be the assigned to emergency calls, voicemail, or conference call services. It allowing multiple users to access the same service without being linked to a single subscriber. Okay, some of the services provided by the VoNR concept are listed here. First is the high quality voice call. Like VoNR enables the high quality voice call over the 5G. Like unlike traditional voice calls in 2G and 3G, which relied on the circuit switch technology, VoNR relies on the IMS to deliver the clear, like low latency voice communication with the advanced codecs like uh, wideband AMB or that kind of codecs it will use to transmit the RTP packets. And next is that video calling over IMS. Since it is integrated with IMS, users can make high definition video calls without needing the third party application. This is particularly useful for enterprises and remote workplaces and ensuring the seamless communication over the 5G network. And next is the SMS over IMS. Like VoNR supports the SMS over IP via the IMS messaging services. And next is the multi-device and multi-access connectivity. One of the advantage of VoNR is it is support for multiple devices and access types. Like it enables IMS voice continuity, allowing users to switch between the different networks without dropping the ongoing call. For example, if a user moves from a 5G standalone network to an area without 5G coverage, VoNR can fall back to that 4G. That is the EPS fallback will happen. It will connect to that VoLT um, VoLT call. Like VoNR works across various connectivity options such as like a Wi-Fi, LTE, and 5G standalone. Okay. And next is the emergency calling. Like it supports the emergency calling, allows users to contact emergency services with a high priority and low latency. This is essential for situations like a medical emergency or any disaster or any accidents. This system also ensures that prioritize the QoS and dedicated networks access to the guaranteed that emergency calls go through even during the network congestion. Like these are the bearers in VoNR. First is the default bearer, that is for the SIP signaling. This is a non-GBR. The default bearer is mainly for IMS signaling, which means it carries the important messages for setting up and managing calls, like all the SIP register and invite and all kind of SIP regarding messages will be transferred over this default bearer. It uses the 5QA5, but it didn't have that GBR. And next is that dedicated GBR bearer, VoNR medium. This bearer is used for actual voice call in the VoNR. It carries the RTP voice packet, like meaning the real voice data during your call. It has a QoS flow of, it has a 5QA1, and importantly, it supports the GBR. So the GBR will ensure that it will uninterrupted voice quality and it will call maybe smooth. And next is that one more is the optional dedicated bearer. This is for the SMS over IMS. Like this is extra bearer used when needed, like for SMS services. It uses the 5QA3, but it's like the default bearer. It doesn't have any the GBR. So in this slide, we will discuss the key protocols used in VoNR. First is the signaling protocol. First, we have the signaling SIP protocol. This protocol is responsible for session establishment, modification, and termination in the IMS. Next, we have that SDP. SDP stands for Service Description Protocol. This protocol defines that media cortex and IP and ports for the RTP streams, and it ensures the proper media session setup. Like when a user caller dialing from one user to another, on the time like one invite message will be transferred between the SIP server and client. So on that time, this SDB inside the SDB we can find some of the parameters like what codecs it will support, and what is the IP of both the users, and what in which port the mobile opened that RTP client. Everything will be sharing this. And next is the media transport protocol. Like for transporting voice packets, we use RTP. RTP stands for Real Time Transport Protocol, which carries that VoNR voice traffic efficiently. Like to ensure the high definition quality voice, and VoNR uses the advanced voice codecs such as that AMR wideband, like adaptive multi-rate wideband. And next is that security protocol. Like finally, in security in VoNR, it ensures the using the IPsec. This protocol ensures the IMS signaling and data connection, protecting the voice traffic from like any threats. Like all the SIP signaling message will be encrypted with IPsec in between the user agent and the client. That means that mobile and that IMS server. In this slide, we will discuss how the SIP communication works between the user agent, that means the mobile device, and the CACF. Like SIP protocol operates using the request response model. User device is called as a SIP user agent, and it sends the request to initiate or manages call, and the network responds with accordingly. There are six core SIP requesters as defined the RFC 3261. First is the register. This is used by the device to register with the network, and the next is the invite. Like whenever the person call to one person call to another person, on the time it will use the invite method. So once the success of this invite message, the call session will be starts. And next is that acknowledgement. Like it used to acknowledge the any successful call setup. And next is the buy message. It's whenever the user want to end the call, on the time this method will become. And next is the options. Like if user want to query the any network supported capabilities, on the time user agent will send the options. And next is the cancel. Like if any of the services want to be ongoing services or requests want to be cancelled, it should be do by the cancel method. Like in the right side, you can see some of the SIP responses. The network responds to this request with different status codes and categories into some different series. One is the 100, 200, like different series they categorized. The 100 series is for the professional, like it's a temporary response. Like whenever the one user want to call to another user, on the time the mobile starts to ring. On the time one protocol, one method is called 180 ringing. So this kind of a provisional response. And another is the successful. The always the provisional response will be looks for that following by successful response. It's not like similar to that final response. And in the final response, like that if any of the request was successful, for that time it will send the 200 OK message. And this we can one of the example is the 200 OK message. Like for the invite message, server will reply with the 200 OK. And next is the 300 series. It is for the redirection. Like a call is being redirected, that kind of a message will be taken care by this response 300 series. And next is the 400. Like any client error happen, the request failed due to any issue on the client side, like even the bad request. So if any kind of if any user want to dial to the another user, but that is not in the same network, on the time it will send with 400 bad request. And so on, like 500 and 600 series also there. This is the In this slide we'll discuss the IMS registration and call setup flow. Like here you can see that this is the calling UE and another is the caller UE. In between the G node B and 5G core network, and it may be it's between the two different the users are between the two different G node Bs. First is the initial setup. This process starts with the RRC connection setup between the UE and the G node B. This establishes the radio link necessary for communication. And next is the QoS flow with 5QA5. It is established for the SIP signaling. This ensures that IMS message can be exchanged between the UE and the IMS network. And this is in this block you can see this IMS signaling and codec negotiation. The IMS system performs the codecs negotiation to determine the optimal codec for voice transmission. This is done through the SIP signaling. Once the codec negotiation is complete, another QoS flow 5K1 and are set up for the RTP media flow. And next is the call establishment and voice transmission. After the setup, the network sends the alerting message to indicate that the remote party's phone is ringing. Once the call is answered, voice data is transmitted as voice frames over the RTP channel. Like, and after the complete of the voice calls, if any of the user want to be terminate the call, when the call ends, the the network releases the QoS 5K1 DRB for freeing up the network resources. It only release that dedicated bearer, that means the 5K1. The default bearer 5K1 will be 5K5 will be continue over the end of this entire registration time. Next, we will move to that 5G network slicing. Network slicing is the key feature of 5G. It enables the multiple logical network to operate over the shared physical infrastructure. This allows services providers to create some dedicated virtual network for some specific use cases. Like why the network slicing is needed. Different applications have different requirements. For example, IoT devices require like it's massive connectivity, but it consumes the low bandwidth. And in the case of autonomous driving vehicles, need ultra like a very low latency, but it should be the more reliable for some critical operations. And some of the entertainment services like gaming and video streaming, it requires the high bandwidth for the seamless performance. By implementing a network slice, like operators can optimize those resources and ensure that each service gets required performance without interface from the application. Like in this, we listed the some of the key components of the network slicing. To enable the network slicing in 5G, there are three major components works together. First is the network slice selection function. Like this NSSF is responsible for selecting the appropriate network slice for a user. Like it interacts with the AMF to ensure that each device is assigned to that correct slice based on the policies and the subscription details. And next is that co-network functions like AMF, SMF, and UPF also will be involved during the network slicing selection. And in the radio access network, like the GNOT must support slicing. Like it ensures that radio resources are allocated across the different slices. This allows the RAN to prioritize the traffic based on the slice service. Here we listed the types of 5G network slices. There are three main types of the network slices are there in the 5G. First is the emWB. Like emWB stands for the mobile broadband. This slide is designed for the high-speed data application. It offering more bandwidth. It supports some of the use cases like streaming high-definition videos, AR, VR, and cloud gaming, and under even remote workplaces applications. We can use this emWB. Like in the emWB ensures the seamless high-speed connectivity and making it ideal for the data-intensive applications. And next is the URLLC. URLLC stands for the ultra reliable low latency communication. This slice is built for applications that require extremely low latency and high reliability. Like it is essential for the some of the MCX mission critical services like autonomous vehicles and like even in the healthcare sector and for the remote surgery and in the industrial automations also they are using the URLLC. And third one is that MMTC. MMTC stands for the massive machine type communication. Like this slice is used for some massive IoT deployments. It handling a large number of connected devices with low power consumption. Okay, now we move to that benefits of network slicing. It improved the resource utilization. Like with network slicing, operators can allocate resources based on demand. Instead of a static resource allocation, operators can dynamically assign to the different slices. Like it will help to prevent the congestion and ensure the better quality and efficiency. And next is that tailored quality of service. Like each slice can be customized to meet specific QoS requirements. For example, emWB slice can be prioritized high-speed data, while the URLC slice ensures the low latency. This flexibility allows the 5G to operate to different applications seamlessly. And next is the iteration between slices. Like one of the key benefits of the network slicing is to ability to provide a complete iteration between the slices. And the fourth point is supports industry specific application. Like different industries have unique network needs. Like network slicing enables telecom operators to create industry specific slices such as some for healthcare industry and another for the IoT and smart cities. Like in the IoT and smart cities, they will connecting some millions of devices together. So on the time we can use the machine type slicing. In this slide, we will go through the signaling flow involved in the 5G network slicing. First, step one is that the registration request. Like the signaling starts with UE, sending a registration request to the network via the RAN. This request contains the requested NSSA. NSSA stands for the network slice selection assistance information. Like this specific the network slices the UE wants to access, and it will during the registration request it will share that network slicing indication as well. And step two is that um, slice information will be exchanged within the core network. Like the aim of interacts with NSSF to determine the appropriate correct slice, and these steps include slice information request and the response. Like in the slice information request, aim of send to NSSF to fetch the slicing policies, and slice information response NSSF replace with available slices based on the UE subscription network policies. And next is the slice selection request and response. The aim of evaluates the UE capability and sends a slice selection request to the NSSF. In this request, it contains the UE slice preference. Then NSSF then sends back to the slice selection response, which provides the best matching slicing for the UE based on the predefined network rules. And following with that, authentication and security procedure will be taken care. And in the and following with that, after the aim of selecting the appropriate slicing for this UE, at last it will send the registration accept message. In the registration accept message between the AMF and UE, it will share that what are the allowed NSSAI and configured NSSA in the core network. These are the parameters it will be shared between the AMF and UE. After completing of these procedures, a PDU session will be happen, and during the PDU session, based on the slice, UPF will prioritize the data and it will send to that appropriate UE. Okay, I completed my session. Is if any queries, I can answer.
Thank you, Venkatesh. And yeah, following this, we are honored to have Dr. Rathinamala Vijay, a technologist at the Center of Excellence in Wired and Wireless Technologies at ARTPARK. She has a strong research background in 5G applications using software-defined radios, SDR, and she was previously postdoctoral research at TU Berlin and has worked extensively on power line communications, BLE mesh, and cognitive radio and IEEE 802.11 AGP networks during her PhD at IISc Bangalore. Her expertise in developing testbed and driving experimental insights makes her a key contributor to 5G advancements. We look forward to hear from her today. Dr. Mala, you can now share your screen and start your session.
Thank you, Ruth, for the kind introduction. Could you see my screen?
Yes, yes.
Yeah. So, thank you. So, in the past few days, we had sit through several interesting course modules and had a clear understanding of 5G architecture. Thanks to Sivaramakrishnan and Venkatesh from Niral Network, And we have also learned several evolving and interesting use cases of 5G networks from Abhijit Lele. And he had also presented 3 research and development programs that are happening in ARTPARK, like drone corridor, digital twin, and intelligent connected vehicles. And when you visit ARTPARK, you'll be able to see some of the setups and demos of these programs. So I welcome all of you. Today, in this module, we will talk about a few of the key technologies that are used to realize practical 5G network, such as millimeter wave communication, massive MIMO, beamforming, cloud radio access network, and cognitive radio. So before diving into each technology, we will see why the telecom industry is moving towards higher and higher generations from 1G to 6G and so on. So that's why 5G and beyond, right? So as the number of IoT devices and mobile devices are increasing every year, the existing generation is not able to provide the coverage and handle the capacity. Also, several new services are needed by the users over the time. So overall, we can summarize at very high level that the new generation cellular network should be able to provide higher data rates for enhanced mobile broadband and low latency for gaming, remote surgery, and remote industrial control operations, and high density of nodes such as like mega gatherings at the stadium should be supported. So now, in order to achieve each of these requirements, we can see what technologies are needed, right? So, and based on this, we can classify those requirements as enhanced mobile broadband, or ultra reliable low latency and massive MTC requirements, quality of service requirements, right? So let us look at the high data rate requirement first. 5G is able to provide 10 times increased downlink rate and compared to 4G, and 3 times increased uplink rate when compared to the previous generations. So when we analyze how 5G achieves a higher data rate, the choice of higher frequencies like FR1 and FR2 plays an important role. And FR2 is the one we call it as millimeter wave band. So large contiguous bandwidth is available in millimeter wave band. And so we will first look at the key technology, that is the millimeter wave communications. So as the name suggests, the wavelength of these signals is of the order of millimeter. And we also see that there is a large contiguous bandwidth of 99 megahertz is available between 60 to 164, and also like 200 to 300 gigahertz, like 100 gigahertz of I mean, we were able to get higher bandwidth in these frequency ranges. And you can see that there are few bands, like for example, like between 57 to 64 are not being used because that is an oxygen absorption band where the electromagnetic waves are absorbed under those frequencies. And similarly, 164 to 200 is like more resonant with water vapor. Apart from that, the rest of the frequency range can be utilized. And 28 gigahertz band is more favorable, more commonly being used, and then further slides we will see why that is the case. And also 70 to 94 megahertz, gigahertz is also quite widely being used. So, but using these higher frequency comes with its own disadvantages, such as propagation losses under rainy conditions and scenarios of large foliage depth. So you can see when the foliage depth is, is 40 meter, that is the square markers, right? So if we look at 77 gigahertz, the loss is around 55 dB. But when we move on to 24 or 28 gigahertz, it's the loss is very much lower compared to the 77 gigahertz. Similarly, under rainy conditions like monsoon season, with 150 millimeter per hour cases, again, if we take 77 gigahertz, it's around 60 dB loss. But when we move to 28 gigahertz band, it reduces to around 30 to 40 dB losses, right? So this is why the 28 gigahertz band is much more favorable, with lesser attenuation, with higher bandwidth availability. But even these losses have to be taken care. So then we need two more technologies like massive MIMO and beamforming, right? So in order to compensate for this large attenuation, we use this combination of massive MIMO and beamforming. So what is massive MIMO? So which is actually using a large number of antennas of the order of like maybe hundreds of antennas are utilized to improve the signal quality and increase the data throughput and enhance the coverage. So when compared to the previous generations where like only up to 20 antennas were used, or more commonly 2x2 or 4x4 MIMOs were used. And apart from that, beamforming is a technique that shapes and transmits the signal. Shape the transmit signal and turns them into a concentrated beam that aims at the user equipment. So in this way, the signals do not travel in all directions and gets attenuated. And at the same time, the amount of power required for transmission can also be efficient. So a signal is transmitted, um, the beamforming, there's also several types of beamforming. That is a dual polarization is also another type of beamforming, where the electromagnetic waves that are transmitted are polarized both vertically and horizontally. And this means the antenna system can transmit and receive signals with two different orientations, which improves the system's ability to handle interference, multipath, and spectral efficiency. So a signal is transmitted. So in this way, we are able to achieve. So what I mean is that the dual polarization helps us to adjust the phase and amplitude of each antenna element in the array, and leads to constructive interference in the desired direction and destructive interference in other undesired directions, so that there is a focused beam on a user equipment, and the signal quality is very good at the desired user equipment, right? So this is what the both MIMO and beamforming can help the millimeter wave communication to achieve lower attenuation and higher signal quality. And this is an example. I mean, this is a recent work on millimeter wave 5G compliant platform. So in this paper is titled I-Beam, and it is the authors have designed a 5G compliant SDR based platform. The SDR that they have used is an X310, and they have improved the sensing accuracy using AI model as well. Here the synchronization signal blocks and burst signals in 5G are used to detect the position of an object between a G-node B and a I-beam receiver. So you can see that, so here is the receiver that they have designed, and this is the 5G G-node B, and there's a beam forming, and there's a beams passing through each object, and then it's been received at the receiver. So based on the received signals, they calculate CSI, channel state information, and SNR will be collected, and then the AI model is used to improve the sensing accuracy. See, in this figure, the objects that are detected are a drone, a car, and a mobile. So the I-beam receives the signal and classifies the object in the path of the millimeter wave. So if you look at the 5G NR data frame, it consists of several synchronization signal bursts. So that is, the G-node B is constantly sending these data frames, and the UEs are receiving it. And each SSB burst consists of 4 OFDM symbols. And these 4 OFDM symbols have a primary synchronization signal, and then the secondary synchronization signal, and a physical broadcast channel that carries all the essential information for the UEs to synchronize, connect, and communicate with the G-node B. So it when we talk about essential information, so what do we mean by essential information? It actually sends the identity of the cell within the network. That is, the cell number or the system frame number will be sent periodically to help the device to synchronize its clock with the network. And also the number of resource blocks available, in the bandwidth available, and the physical carrier allocated to the user equipment. All those details are sent in this physical broadcast channel. And it also tells the UE when it can attempt to connect to the cell. And it periodically sends some reference signals and what is the current modulation schemes used, and so on. So every NR radio will listen to this physical broadcast channel when it first powers on, or it loses connection with the base station, and then when it enters a new cell, it listens to this PBCH signal and try to connect to the base station. So next we look at the low latency requirement. So there are several applications that need low latencies, like remote surgery, gaming, and so on. So in order to achieve this requirement, 5G uses flexible OFDM numerologies. So OFDM is the orthogonal frequency division multiplexing with several orthogonal subcarriers. This modulation scheme is used to mitigate the multipath fading And this was introduced in 4G and it is still used in 5G networks, but with more flexibility in subcarrier spacing as opposed to a fixed 15 kilohertz subcarrier spacing in 4G. So here we can, in 5G, we can design for 30 kilohertz subcarrier spacing or 60 or 120. That is the factor of 15 kilohertz. So we have that flexibility. So when, so you can see that in the first one, 15 kilohertz subcarrier spacing is used. In the second row, 30 kilohertz is used. So it is always the multiples of 15 kilohertz. And it goes on as a multiples of 15 kilohertz. So this, while using such a flexible OFDM numerology, what can we achieve, right? So let's take the 15 kilohertz subcarrier spacing. The number of OFDM symbols in a for a user slot is like 14 OFDM symbols, and it is fixed. So so when a second user has to be scheduled, the second user have to wait for about 1 millisecond to get his turn. But when you use 30 kilohertz subcarrier spacing, the first user finishes his session. I mean, in case if he finishes his session within 0.5 milliseconds, then the second user can be scheduled in a half the time when compared to using the 15 kilohertz subcarrier spacing. All the more if you use 240 kilohertz subcarrier spacing, then the second user have to wait only for 62.5 microseconds. So this is how we are able to achieve very low latency in 5G network when compared to a 4G network. And apart from that, in 5G, we have the flexible time domain, time division duplexing configurations, which has flexible symbol slots. So there are fixed downlink slots and uplink slots. In addition, we also have flexible symbol, which can be configured as downlink or uplink. And this is crucial for efficient spectrum utilization. And these configurations may vary depending on the deployment scenario for every cell. So the device can negotiate with the base station to use a specific TDD configuration, because that suits its environment and its application. So it can negotiate. So in this figure, you can see that there is, the first one shows the cell specific pattern, and the second one shows the device specific patterns. And then after negotiation, they arrive at a semi-static pattern which suits both the cell as well as the device, because the cell has to provide multiple users, right? So but it can, within the flexible symbol slots, it can adjust and provide the requirement of a device. Device here means the user equipment. So next we can move on to high density of nodes requirement, right? So in this case, large number of nodes have to be connected to the 5G network within a small area such as a square kilometer, which is very common in large gatherings in a stadium, right? So here, so what are the technologies that can support it? If you look at it, the base station transmission power can be reduced. Like we can use small cells or pico cells instead of a macro cells. So what happens is that in this case, the base station transmission power can be reduced in small cells, and then it can connect to nearby user equipments. So instead of one high powered base station giving coverage to thousands of UEs, you can have several low powered base stations or small cells that can give coverage to many UEs. At the same time, we are reducing the interference among the cells because we have reduced the power. So energy consumption is also going down. Apart from that, we are setting up distributed antenna system across the cell to, like, for example, at every pole in the stadium, you can have a radio unit which can provide a certain range of users, right? So towards that, we have this technology called cloud radio access networks. So let's see what do we mean by cloud radio access networks. So you must have learned from the previous sessions that 5G consists of major components like core network and then G node B and the user equipment, right? So the G node B can be classified into baseband unit and remote radio unit, and this baseband unit can be further classified into distributed unit and the centralized unit. So you can see at this figure, and the centralized unit performs the higher layer functionalities like PDCP and SDAP and so on. And distributed unit performs lower layer functionalities like 5-layer functionalities or radio link control, and MAC layer functionalities is also taken care in DU. So that radio units can be placed quite far away from the core, and DU can be placed much closer to the radio units. So a G node B is divided into RU, DU, and CU. But RU is the radio unit, and DU is the distributed unit, and CU is the centralized unit, right? So you can see even in this picture, the radio unit is shown here, and the radio unit is connected to DU with the front hall. That the communication link between the DU and the radio unit is called front hall, and the communication link between CU and the DU is called the mid hall, and the communication link between CU and the core network is called the back hall. But what do we mean by these? I mean, in general, the communication link used are the optical link or the millimeter wave communication or Ethernet are the common communication links between these components. And why do we have to segregate this G node B into separate components? There is a reason for it, is that the capital expenditure goes down, the operating expenditure also goes down. So for example, there can be many vendors who will specialize only in the DU, and some of them will specialize only in the CU. And the private network, if someone has to implement a 5G private network, he can choose his own CU-DU combination based on his investment, what kind of investment he can make. He can choose these components, which are all 5G compliant as well, right? So that is the benefit of using cloud radio access networks. At the same time, let's say in this scenario, if the okay, so let's say in the second remote radio unit is connected to two user equipments, and those two user equipment has moved away, and there is no user equipment being connected to the remote radio unit, and we can switch off that radio unit so that the energy consumption can be reduced further, right? So these are some of the benefits. And if you are wondering how these units will look like, then the centralized unit will look like a CPU or a server, and it performs functionalities like SDAP, PDCP, and remote radio control layer functionalities. And distributed unit also may look like a server, and it also have ports for synchronization and communication links like Ethernet ports, optical ports, or millimeter wave communication. Antennas can be connected to the ports shown here. Yeah. So on the right hand side, you are looking at the radio unit, commercial radio unit, and there is a antenna. Yeah. So the commercial radio unit is there, and this is the lab radio. Yeah, sorry for the interruption. So to have, so the right hand side shows the two figures of commercial radio unit and the lab radio, where the antennas are of cheaper antennas, and then so based on the scale of your private network, you can design your radio units. Next, we move on to network slicing. I think much of it is covered by Venkatesh as well today. So you can see that enhanced mobile broadband has a separate slice represented by the blue link, and then massive IoT slice is represented by the light blue slice, and the dark blue slice is provided for the medical infrastructure and the automotive, where very ultra low latency quality of service is required. So in this case, the user equipment always sends its requirement in the form of a packet called SNSSAI, which stands for Single Network Slice Assistance Information. So this packet is 32 bits, and 8 bits represents the slice or service type, and the 24 bits are used to represent the slice differentiator. So this gives so in order to differentiate two slices having same slice type, slice differentiator is used. And slice type, the major types we have discussed is only 3, but there are also room for supporting larger number of slice types, which has 8 bits, right? So it's 255. I mean, you can support more number of slice types other than your EMBB, URLLC, and ultra reliable low latency cases. And the very common slices which are coming up is like vehicle to infrastructure, or HMTC, which is used for high mobility cases where the mobility of the users is predicted to be more than 100 to 400 kilometers per hour, and so on, right? So, and other than that, there's also major technology called cognitive radio, which is very much useful in interference management and radio resource allocation. So this is a technology where radio has the capability to sense the environment and decide on the transmission parameters. So using this technology in 5G, it is very useful to allocate resources. So if you take the non-standalone mode cases, the spectrum is shared between the 4G LTE and the 5G. So the spectrum efficiency has to be done using both the spectrums. So based on the current traffic conditions and the user, the cell capacity and so on, right? So everything is taken care, and then based on that, the spectrum allocation is done. Similarly, in the case of heterogeneous networks, there are macro cells, small cells, picocells, and femtocells, right? So how much resources have to be allocated to among the these cells, and how efficiently they can use the spectrum can be, I mean, all this can be achieved using the cognitive radio. And this is also bringing in a new type of networks called self-organizing networks, with like radio acquires a lot of information, and with the help of ongoing AI models and everything, we can use the current network conditions and interference levels and user demands and decide on the transmission parameters, frequency hopping, and everything. And there's also a that currently the 5G non-terrestrial networks is evolving with a fast pace. And so non-terrestrial networks is a network of low Earth orbit satellites, medium Earth satellites, or geostationary satellites, and high altitude platforms and drones to provide large global coverage. And this network is especially useful in the cases of disaster management, when terrestrial networks are completely affected due to earthquake or tsunami, or it can be due to war conflicts and so on. So all during those situations, the users can be given a connectivity which is much needed. And also these networks acts as backup and redundant networks when there is sturdy terrestrial network, but still these non-terrestrial networks can be used as a redundant network to give a resilient network coverage for certain class of slices, and certain quality of service have to be maintained. Then we can bring in this non-terrestrial networks integrated with the terrestrial networks. So this is an example of integrated terrestrial networks, and you can see non-terrestrial network gateway which is being connected to the core, and that transmits the 5G signals to the satellites. And there's also optical link between the satellites to communicate and to arrive at a global coverage, and back, I mean, vice versa, like the signals from the non-terrestrial networks are received to the 5G core. So cognitive radio is widely used in this context, So though there are works on terrestrial cognitive networks, non-terrestrial networks is evolving. I mean, non-terrestrial network cognitive radio is evolving. And this paper, this is one of our current work where the cognitive radio is used for the critical infrastructure protection, where the utility company is able to collect information from remotely located wind turbines. And this is feasible via a satellite, and the resilient communication between the satellite and the ground station is achieved by the cognitive radio technology. So these are some of the frequency ranges supported by 5G. The FR1 for NTN and FR2 for NTN are shown. You can see that 28 gigahertz, which has N510 to N512, is allocated for non-terrestrial networks. And similarly, S-band and L-band are used in FR1 for the non-terrestrial networks. So you can see that the key technology that is, I mean, we have so far seen the key technologies for 5G, but as we move on to 6G, what we can see is that the millimeter wave will move towards the terahertz communication bands to achieve much higher data rate and low latency. And similarly, the cloud radio access network will move to Open RAN solution. That is where a radio access network will evolve with many open standards that define the interfaces between DU and CU and DU and RU and so on. In 6G, we will also see that we'll be moving from orthogonal frequency division modulation scheme to orthogonal time frequency space techniques to get good performance under time varying channels. So for example, when under mobility, where there is a lot of mobility is involved, such as drones or communication of the nodes while moving in train and so on. The modulation schemes, upcoming modulation schemes are moving towards OTFS. And terrestrial network cognitive radio will be integrating, I mean, along with the terrestrial cognitive radio, we will also be using non-terrestrial cognitive radio. So, so that's the end of my talk, but I'm looking forward for the participants when they come to ARTPARK. So we will be able to show several demos, and the 2 dedicated days we are setting up several hands-on sessions at ARTPARK where you can play around with 5G modules, and you can connect to our existing core network. One is the commercial, you can connect to the commercial radio, as well as you can connect to our lab open source radios. And I hope you will enjoy those 2 sessions, and looking forward to see you there. Yeah.
Thank you, Dr. Mala. So any questions from the participants?
Hello.
Yeah, yes, Bikash.
Yeah, hi, ma'am. So I had asked my question that can we use 60 gigahertz V band, ma'am, for this millimeter wave?
So as we saw in our earlier slides, right, 60 gigahertz has the oxygen absorption band, right?
Yeah.
right? So oxygen molecules resonates, and then kind of because of this, it gets absorbed. The electromagnetic waves undergoes severe attenuation, and that's the reason we won't use 60 gigahertz quite often. I mean, that's what the literature shows, and you can also refer to this article here. And also similarly, the band between 164 to 200 gigahertz is also supposed to be not very commonly used because of that. Yeah.
Okay. Ma'am, why I asked this question, because I am basically responsible for designing the railway and metro systems, and currently we are planning to propose one high-speed metro for the Saudi Arabia. Okay, so there we are in touch with many OEMs. So
Okay.
one of the OEMs claimed, it's from UK. So they claim that they have tested with the 60 gigahertz V band, and where they have achieved more than 2 gigahertz at the speed of 300 kilometer per hour.
Hmm.
Because high speed train will run at 300 kilometer per hour. So they have tested it,
Mm-hmm.
and they mentioned that they are implementing it also in the UK. So that's why I asked this question.
Okay, so in that case, like as I mentioned, right, this has this inherent problem, but with the help of advanced technology, like having thousands of antennas or hundreds of antennas and using massive MIMO technology
Mm-hmm.
and beamforming, you can
Yeah.
design it, right?
Okay. Okay.
And reduce those losses even at those frequencies, and that is why you're able to
Yeah.
right.
Okay.
So,
Okay. Thank
and it's very good to know, good that you have shared that information for the
you.
audience. Yeah.
Yeah. Okay.
Do we have any more questions?
Hello, ma'am.
Yes, Gangadhar, you're audible.
In the beamforming, is 5G passed through the obstacles like buildings, trees, and vehicles?
Can you be a little louder?
In beamforming in 5G, is that passed through the obstacles like trees, buildings, and vehicles?
In general, it gets reflected. Yeah.
Informing he asks how 5G can be used.
Yeah, so beamforming in general shapes the transmit signals towards the user equipment. Instead of, so you send several signals, but their constructive interference will be finally focused on the desired location, right? So that is the main motivation behind the beamforming. So there can be reflections, but finally the interference due to those multipath, right? When it hits the tree or the nearby objects, it gets reflected. But at the user equipment, they all are received, but they are received with higher constructive interference. Like it will kind of enhance the signal quality. So that such will be the design of MIMO as well as the beamforming.
Ma'am, if beamform is become failure because of the obstacle or UE mobility, is there any method to know, like how, because of what reason that beam was failure?
So yeah, as I mentioned in these thing, right? So you can have this is ISSB 0 to ISSB n minus 1, right? So you have, these are all for a particular angle. So when you receive these information, in the 4 OFDM symbols of every SSB burst, you will know the information, that is the channel state information, each beam, what it has undergone, and what is the channel state of each beam can be obtained at the G node B. You can get it. As well as if you design your user equipment, you can also get all these informations. Yeah. You should have the logs of those ISSB signals. Then you'll be able to know why that particular beam has not given a good signal quality and so on.
Okay, ma'am. Thank you.
Ma'am, because you said again, I have one more question. Do you think that beam forming is realistic, or it is good to implement in the directional traffic? Like I think for the distributed traffic where traffics are moving in left, right, or east, west, the number so there beam forming is useful. But for railway network where you have fixed track and train is moving in only one direction, so do you think beam forming or
Yeah, so mostly controlled environments, it is easier to design. But with the help of upcoming AI and everything, even with the unknown environment, you can adapt. You can add more different cases, and the system will try to learn those things and get adapted to a new environment.
Okay. Ma'am, regarding this DU and CU, so you mentioned that it is better to keep DU near the RAN.
Yes.
Yeah, but no, I will talk about the FRMCS. You might be knowing for the railway, UIC has implemented one technology, that is FRMCS, which is based on 5G. So
Okay.
to reduce the cost, what they have recommended that we can play there are three technologies, correct? What you have recommended is correct, but they have to reduce the cost. We can place CU DU in the remote area, and then we can extend RAN till the 15 kilometer, like placing RU at every 2 or 3 kilometer based on the terrain. So, so is it a good way to implement, or you still suggest that DU should be near to RU?
Okay. So in your case, I would say that this may be because in order to reduce the cost, there can be one DU can support multiple RUs, right?
Yeah.
So such is the case according to your application. So that's why according to the application also, this can be the structure of G node B can be is flexible. So you can always change it according to your application. And can you mention what is your distance between your distributed unit and RU in your current application?
Yeah, so ma'am, what we are doing, we generally place it along the track area. So there we put the prefabricated shelter. So suppose I have placed my shelter in which I have placed the CU DU with routers at suppose a distance 0, and from that 0 every 2.5 kilometer or 3 kilometer, that is based on the terrain. If it is too dense, then I have to reduce the distance, because my train speed is more than 300 kilometer per hour, correct? But right now what we are considering, it is at every 2.5 kilometer we will place. And the second prefabricated shelter where I will place this, it will, the distance between 0 to next shelter will be around 12 kilometers.
Okay.
Okay.
Okay. So maybe from 2.5 to 12 kilometer, you can vary.
Yes, yes. So in between that shelter, two shelters, I have to place RU at every 2.5 kilometers.
Okay. Okay.
And it will be duplicated because it's a mission critical where your railway is running completely on this network. So we are providing dual coverage. So if still one fails, second will.
Mhm.
take over. Yeah.
Okay. So when you say shelters, is it like
Prefabricated
mitigation
shelter, it's a kind of
boxes?
PVC fabricated rooms are there which you can install.
Okay. Okay. That's very nice to interesting
Yeah, yeah.
session. Yeah.
Okay. Thank you.
Any more questions? Okay. So this brings us to the end of day 4. Thank you again to Mr. Venkatesh from Niral Networks and Dr. Mala from ARTPARK CoE WWT for their valuable insights today. And a few reminders before we close. So for the participants, we are maintaining attendance record. So please ensure you're present for the session at time. And if you have any clashes with the session timings, we appreciate your patience and request you to attend online session as much as possible. For future courses, we'll be happy to incorporate your feedback on timing adjustments. So apart from this, no, not for this tutorial on 5G essentials, but for the next course that we conduct, we can take up your feedback on timings. So we have day 5. Day 5 is on Friday. So please be on time and please attend the session from 3 to 5. Don't forget to fill out the form for doubts and clarifications that has been shared with you. And now I'll be sharing you the link for this session. If you miss out any part of the session or you want to, rehear the session, you can use it, but this is only for the registered participants. So for now, we don't want to disclose to the public. Yeah, thank you everyone for the speaker and also for the participants. Looking forward to see you all again. Have a great evening. Thank you. Thank you all. Bye.